In this video, we're going to be looking at the centre of mass question from MEI M3 2016. The question states, the region R, shown in figure 2.1, is bounded by the curve y equals k squared minus x squared for 0, x being greater or equal to 0 or smaller or equal to k, and the coordinate axes. The x-coordinate of the centre of mass of the uniform lamina occupying the region R is 0.75. Because it's uniform, we only have to consider the area rather than the mass. So if we consider the area, we take the moment of area for small segment of the lamina with thickness dx, and we take the moment from distance x. And we sum this up from 0 to k. That would give us the moment of the whole lamina, and then we're going to compare that to the center of mass moment, which is going to have mx bar. That's the moment of the total lamina, and then we compare that to 0 to k x and y dx, because the area is going to have height y and a thickness dx. That's the small area, and then taking moment and then sum it up from 0 to k. Now, if we have that, n, which is, as I said, row A, but we're not going to consider row because it's all uniform, so we're going to consider A. The area is actually just the integral of y dx over 0 to k. So which is going to, x bar is just going to be equal to integral of x y dx over, over integral of y dx. And that's going to give us k squared x minus k squared x to the square root of 2, minus x to the 4 over 4. But that's the wrong sign. We should reuse the round bracket in here because we've already evaluated it. Now, if we take the integral, if we put 0, it's going to be equal to 0. So we're only going to consider k, and we just sub it in. K to the 4, k to the 4. And then here it's going to be k to 3 minus 1 over 3, k to 3. So now, if we try to write that down, I don't know how to erase it, in the exact form, we're going to get k to the 4 out of 4 over 2 over 3 k to 3 is equal to x bar. We know that x bar is 0.75, it's equal to k 3 over 8, and that's equal to 3 over 4. Equal, isn't it? Yeah. And therefore, k is 2. Now we've done the first part, we're going to look at the second part now. Okay. Delete. So, we're looking at, if we draw the diagram again, x, y, z, now with the 3D shape, it's going to have this circle here, and it's going to have this shape. So that is going behind. Now, we use the same principle as here. We take this small disk with thickness dx, and because it's a disk, it's going to have a volume of y squared, because it has radius y, times dx times pi. That would give us the area, no, the volume of the small disk And then if we sum that up and we take the moment and then sum that up. 0 to k, that's going to equal to the moment of the volume from x bar. So x bar is going to be equal to the integral of 0 to k x y squared dx pi over the volume, which is just the whole volume, which you probably have learnt, 0 to k y squared dx pi. Now, the pi's cancel out, so if we simplify that, we get x bar is equal to integral of x y squared dx over integral of y squared dx. Now, y squared is just k to the 4 minus 2k squared x squared plus x to the 4. And then if we just do it, then we get k to the 4x minus 2k squared x to the 3 plus x to the 5 integrated over integral of k to the 4 minus 2k squared x squared plus x to the 4 dx. And that is equal to k to the 4x squared over 2 minus k to the squared x to the 4 over 2 plus x to the 6 over 6 from k to 0, and then k to the 4x minus k 2k squared x to the 3 over 3 and plus x to the 5 over 5 k to 0. And for when x equals 0, it's all going to be 0 because all the terms have x. So if we evaluate that, then we get k to the 6 half minus half plus a sixth over k to the 5 1 minus 2 over 3 plus 1 over 5. That is equal to 1 over 6 over 8 over 15. That is equal to 15k over 48. Now we know that k equals 2 in this case, so that's equal to 30 over 48, which simplifies to 5 over 8. And we get x bar equals 0.625. And because we know that this whole shape is rotated from about the x-axis, the y symmetry is going to have us